The principle of work and energy offers a formula which can be used when determining a parameter of a particle in motion. Check how this is used here in dynamics of rigid bodies. The principle of work and energy is derived from the Newton's second law of motion that force is mass times acceleration. In varied motion, the force considered is the one moving along the path, which is called tangential force. So acceleration is also tangential. Focusing on acceleration, the basic motion equation of relating acceleration and velocity is AdS equal to VdV. This can show that tangential acceleration is VdV all over ds. We substitute velocity into the Newton's equation and have tangential force times the derivative of s is equal to mass times VdV. Take out the d's in the equation by integration to have the tangential force times displacement s is equal to m times the square of velocity all over 2. We can have this written as F times S equal to half of mv squared. And since we integrated, there are limits to incorporate, like S is within S1 to S2, and velocities from the first velocity to the second. So take out limits to have the equation F times S2 minus S1, and this is equal to half of m times V2 squared minus V1 squared. S1 is actually 0, as this would be the starting point of any situation. So we have the tangential force times S is equal to half of its mass times the velocities. And then, the tangential force can be computed as the total applied force times cosine of theta. Thus, the work-energy equation comes out as force times cosine of theta delta x is equal to half of mv2 squared minus half of mv1 squared. The left side is work, and the right side of the equation is kinetic energy. With the long equation, this can be reduced in terms like the work side of the equation can be tagged as the summation of work from points 1 to 2. Half of mv2 squared is t sub 2, and the other mv term can be tagged as t1. Transpose the last term to the other side to have t1 plus the summation of work from points 1 to 2 is equal to t2. In situations that friction is present, the work-energy equation still remains the same. Although the summation of forces would have added friction, that would make the term force applied less friction. And these two forces can be written as the force times the change in displacement minus the work of friction, which can be solved as the coefficient times the normal force multiplied by the change in displacement. The work-energy equation can then be rewritten as half of mv1 squared plus force times the change in x minus mu times the normal force times the change in x is equal to half of mv2 squared. The first example involves a 2-ton truck which is traveling an inclined road of 10 degrees with a speed of 4 meters per second. At one instance, the driver hits the brakes and we are to determine the distance until the truck totally stops. The coefficient of friction is 0.35. First is to draw the free body diagram. The truck is inclined at 10 degrees and it is going down the highway at 4 meters per second velocity. Draw the weight of the truck at its center of gravity and it's pointing downwards. The weight is 2,000 kilograms times the gravitational pull of 9.81, giving 19,620 newtons. The component of weight which we should consider is the one parallel the incline. The other force to evaluate is because of the friction. Friction is computed from the normal force, and F of n is derived from the weight, but perpendicular from the incline. With the work and energy equation, we identify the different parameters. Force is taken as its x component, and that is the weight of 19,620 times sine of 10 degrees, resulting to 3,406.98. The normal force is computed as F cosine theta, or 19,620 cosine of 10 degrees to have 19,321.93 newtons. Plug the values into the work and energy equation to have half of 2,000 kilograms times the square of velocity 1, which is given in the problem as 4 meters per second, then add F of 3,406.98 times delta x less friction computed as 0.35 times the normal force of 19,321.93 times the change of displacement. This is equal to half of 2,000 times the square of the final velocity taken 0, as the truck stops after the driver steps on the brakes. This long equation is simplified as negative 3,355.7 delta x is equal to negative 16,000, where delta x is computed as 4.768 meters. The same problem can be computed using Newton's second law of motion. From the formula net force is equal to the mass times acceleration, we can break down the force as applied minus friction. Similar with the computed values earlier, we get force as 3,406.98 newtons and normal force as 19,321.93 newtons. Place the values in the equation and compute for acceleration as negative 1.6778 meters per square second. Knowing acceleration, we use one of the motion formulas to find displacement. We take the square of final and initial velocity equated with the acceleration and displacement. Again, final velocity is 0 and initial velocity is 4. Acceleration is negative 1.6778, which can be simplified as 3.3557 s as 16. So the truck stops around 4.768 meters from the moment the driver stepped on the brakes. The second example discusses a crane lifting a 1,000 kilogram beam with the force equated as F equal to the quantity of 28 plus 3s squared in kilonewtons. One task is to find the speed of the beam upon reaching a distance of 3 meters. The second task of which is the time it takes the crane to lift the beam this height. In the free body diagram, it would be easier to identify the unknown parameters from the given. The weight is taken as 9.81 times 1,000 kilograms to give 9,810 newtons. From the work energy equation, identify initial velocity as 0, making mv squared as 0, thus t sub 1 is 0. The summation of work comes from the work due to the applied force and weight. Work due to F is given as an equation, so this should be integrated to have it simplified. The integral of the quantity of 2,800 plus 3000 with s squared ds is 2800 s plus 3000 s cubed all over 3, which can be simplified as 2800 s plus 1000 s cubed. The other type of work in the system is that which comes from the weight, which is equal to 9810 s. The last term from the work energy equation is T sub 2. Again, with the same energy equation, half of mv squared with a mass of 1000, we get 500 v squared. With the three terms already identified, plug each into the work energy equation to have 0 plus 2800 s plus 1000 s cubed minus 9810 s is equal to 500 v squared, which can be simplified as 500 v squared is equal to 1000 s cubed minus 7010 s. From this point, velocity is then computed as the root of 1000 s cubed minus 7010 s all upon 500. So if we let s equal to 3 meters, we get the velocity as 3.455 meters per second. For the time it takes to lift the beam to a height of 3 meters, we use the formula for velocity equal to ds all over dt. We take t by integrating the whole equation, where the limits for s are from 0 to s equal to 3. By plugging 3 for s, we take t as 3 all over the velocity of 3.455 to give 0.87 seconds.